Okay, in today's lecture, we're going to cover the first part of the section 6.6 material on parametric surfaces and surface integrals. So in this first part of the lecture, we will just talk about parametric surfaces and some problems involving parametric surfaces. So let's introduce the concept of a parametric surface. If we think back to our chapter 3 material, we recall that we can define a space curve, that is a curve in 3 dimensions, by making use of a vector function, r of t, which had component functions x, y, and z of t, where this function depended on some parameter t, maybe representing time. Now, in this section, we're going to introduce the same sort of concept, but where we are describing a surface in 3 dimensions rather than a curve. And we see that surfaces can be described by a vector function, r of u v, which has component functions, x, y, and z, which depend on 2 parameters, u and v. So these sorts of surfaces are what are called parametric surfaces. So our definition here, any surface, let's call it S, which can be described by the vector function r of uv, which has component functions x, y, and z of uv, where the parameters u and v vary throughout some region D. This is what is called a parametric surface. So the way that we can think about this surface is in the following way. If we consider our parameters, u and v, varying over some domain in the plane, so let's say we have in the uv plane some domain D, and we choose some point, let's call it uv, that lies within that domain, we can think about our surface as being traced out by the position vector r of uv. So if I substitute this point uv into my vector function, I get a 3-dimensional vector, so I could draw its representation as a position vector, so that is with the initial point at the origin, and I get some vector in 3 dimensions. So as I choose different points in this domain D, and I draw out the different position vector representations that I have for those for the vector I get by plugging those points into my vector function, I get different points being traced out over a surface S. So these parametric surfaces are useful in describing certain types of surfaces which can't be easily described as the graph of a function of 2 variables. So to familiarize ourselves with parametric surfaces, let's look at an example where we are asked to find a parametric representation for a given surface. So a lot of problems that we're going to see in the last part of chapter 6 require us to describe a certain surface using parametric equations. So as an example, in part A, we're asked to find a parametric representation for the paraboloid z equals x squared plus 4y squared. So this is an elliptic paraboloid. Maybe we could visualize it here. So in space, we have our x and y axes, and then a z-axis oriented by the right-hand rule. And this surface is an elliptic paraboloid. So it has its vertex at the origin, and it's opening upward from the z-axis, and its cross sections are ellipses. So we have some surface that looks like this, and we want to find a parametric representation for a surface. So this type of problem, where the surface is the graph of a function of two variables, here z is a function of x and y, so this type of problem has an easy parameterization. So we need to choose how we're going to define x, y, and z in terms of u and v, these parameters. So anytime that we have the graph of a function of x and y, an easy parameterization is to let x simply equal u and let y equal to v. So then immediately our equation in terms of u and v to describe z, well, since z is x squared plus 4y squared, we now just have u squared plus 4v squared. So a parametric representation for this surface would be given by the vector function r of uv, which is equal to the vector whose component function, so our x equation was u, y was equal to v, and z was given by u squared plus 4v squared. And in a lot of these problems, we need to specify what the parameter domain is. That is, what is the set of valid values that we can choose for u or v. Now, for a paraboloid, there are no restrictions on what we can choose for u or v. So we might have a little statement here where u and v could be any point in the real plane. So x and y or u and v could be any real numbers that we want here. So let's look at another example that's maybe a little bit trickier. So in our second example, we are asked to find parameterization for the part of the cylinder, x squared plus y squared equals 9. So that is a circular cylinder of radius 3 extending along the z-axis, which lies between the planes z equals 0 and z equals 5. So before we find our parameterization, let's think about sketching this surface. So here we're talking about part of a cylinder of radius 3, circular cylinder here, that lies between two planes z equals 0 and z equals 5. So here we have part of a circular cylinder. Its radius is 3. And it's lying between two planes. The lower plane corresponding to z equals 0, that is the xy plane, and the upper plane, z equals 5, that is the plane which is parallel to the xy plane but 5 units above it. So here the height of this part of our cylinder would be 5 units. So since we are talking about a surface which is part of a cylinder, rather than making use of rectangular coordinates, x and y, it stands to reason that we might use cylindrical coordinates to describe part of a cylinder. So if I were to use cylindrical coordinates here, let's think about how we could define points x, y, z in terms of cylindrical coordinates. So we know that x would be given by r times cosine of theta, but in this example, we had a radius of 3 for this cylinder. So r here is 3 times cosine of theta. Y, in terms of cylindrical coordinates, is given by 3 times sine of theta. And z, in terms of cylindrical coordinates, is just equal to the rectangular coordinate z. That is how far we've moved above or below the xy plane. So a parametric representation for this part of our cylinder would be given by r of, here instead of u and v, we were using theta and z as our variables. So here we might say r of theta z would be the vector whose first component, which describes x, is given by 3 cosine theta. Y is given by 3 sine of theta. And z is simply equal to z. And if we need to describe a particular part of this cylinder, we need to describe the range of our parameter values. So in this case, we were talking about part of this circular cylinder, so we do want a full revolution around our circle, which means that our theta value would lie between 0 and 2 pi to get one full rotation around our cylinder. And our z value would range from the lower plane, z equals 0, to the upper plane, z equals 5. So we might say that z also needs to lie between 0 and 5 to describe the particular part of the surface that we're interested in for this problem. So let's look at another one. In this last part, we are asked to find a parametric representation for the part of a sphere. X squared plus y squared plus z squared is 36, so sphere centered at the origin of radius 6, which lies above a cone given by z equals the square root of x squared plus y squared. So here again, let's maybe sketch our surface first. So we're looking at part of a sphere which lies above a cone. Let me maybe start by drawing my axes so we can visualize this a little more precisely. So in space, we have our x and y axes, and then a z-axis. And we are looking at part of a sphere that lies above a cone. So let's start by sketching the graph of our cone. Z is the square root of x squared plus y squared, so that is the upper half cone, where z is the positive square root. So we have something that looks like this. And we're looking for, more precisely, the part of the sphere of radius 6, centered at the origin, that lies above that cone. So if we think about our sphere of radius 6, well, we have, if we draw the top half of it, some sphere of, or upper hemisphere of radius 6. And we want just the part of that that lies above that cone. So we see here, well, okay, our upper half sphere is going to intersect that cone in a circle. So we're talking about some cap of this upper hemisphere that we're trying to describe. So in order to describe this surface, since we're talking about a part of a sphere which lies above a cone, we might make use of spherical coordinates. We had introduced the idea that equations of spheres and cones in space are described pretty easily in terms of spherical coordinates. So if we were to make use of spherical coordinates to describe this surface, well, let's think about how points on this surface would be defined. So points x, y, z in terms of spherical coordinates are given by the following. X is equal to rho times sine of phi times cosine of theta. But here we have a sphere of radius 6. So rho would be 6. So we're going to have 6 sine of phi cosine of theta. Y, in terms of spherical coordinates, is rho, which in this case, sphere of radius 6, times sine of phi times sine of theta. And z, in terms of spherical coordinates, is given by rho, which is 6 times cosine of phi. So here, a parameterization for our surface, r, in terms of the parameters phi and theta, would be the vector whose x component is 6 sine phi cosine theta. The y component is 6 sine of phi sine of theta. And the z component is 6 cosine of phi. And now we need to specify what our parameter range or our parameter domain would be to describe this part of the surface that we're interested in. So here, since we're talking about the cap of a sphere, well, we're looking at a full rotation around that cap of our sphere. So we have theta lying between 0 and 2 pi. And our phi value, well, let's think about where phi can range from. Remember, phi represents the angle measured downward from the positive z-axis. So here, if we have our positive z-axis, we can rotate downward from there until we hit this cone. Because remember, we need specifically the part of the sphere that lies above that cone. Now the cone that we're describing here, z equals the square root of x squared plus y squared, has an angle of 45 degrees, or pi over 4 radians, measured downward from the positive z-axis. So here, our phi value could range from 0 to pi over 4 to describe that particular part of the cone, or the particular part of the sphere which lies above this cone. So the next thing that we'll start considering, now that we have some work or some familiarity with parameterizing a surface, let's look at some problems involving parametric surfaces. So one problem of interest that we saw a little earlier in the course was finding the tangent plane to the graph of a surface or to a surface at a specific point. Now, if we have parametric surfaces instead of the graph of a function of x and y, we need a new way to find our tangent plane. So let's think about how we're going to do this. So let's suppose that we have some parametric surface S, so shown here in blue. So it may not be the graph of a function. And we are interested in finding the equation of a tangent plane to that surface at a point P naught. So here's some point P naught that lies on our surface, which has a corresponding position vector r of u naught v naught. So for some specific point u v, we'll call it u naught v naught, when I substitute that point into my vector function r, I get a position vector which corresponds to that point. So here, this is the graph of the position vector, or the representation of r of u naught v naught. So it defines some point on my surface. So how can we find a tangent plane to this surface? Well, here's one way that we could think about it. If we were to hold u a constant by setting u equal to u naught, then if we think about the function, the vector function r of u naught v, this is now a vector function of a single parameter v. So this vector function of a single parameter defines a space curve C1, which lies on our surface. The reason it lies on the surface is because our u value was taken to be u naught. And as v ranges over its range of values, we get a curve C1, which lies on the graph of our surface. Now, in the same way, if we were to hold v as a constant by choosing v to be the fixed value v naught, then as u varies over its parameter value, we get another curve C2, which lies on our surface. So we get some other curve here, C2, which lies on our surface, and both of these curves, C1 and C2, pass through the point P naught, because the point P naught corresponded to U equal to U naught, V equal to V naught. So if I want to find a tangent plane to this surface, well, let's think about what we could do. If I were to take the partial derivative of our vector function r with respect to v at the point u naught v naught, that defines a tangent vector to the curve C1 at the point P naught. So if I look at the partial derivative with respect to v at this point P naught, I get a tangent vector, which would be the partial derivative of r with respect to v at that point. And in a similar way, if I were to look at the partial derivative of r with respect to u at the point u naught v naught, that defines a tangent vector to the curve C2 at the point P naught. So from that point P naught, if I take a partial derivative with respect to u, I can find a tangent vector to that curve C2. So these two vectors, which I just found that I've shown here in green, how can we use these to find the tangent plane to our surface? Well, we know to find the equation of a plane, we need a point within that plane. So here we're given that point P naught, the point on our surface, and we need a normal vector to the plane. So these two tangent vectors which we found, if we were to take their cross product, we get a vector which is orthogonal to both of those. We would have a normal vector, let's call it n, which could be defined as the cross product. Let me maybe show this in a darker color. And n would be the cross product of these tangent vectors. That is the cross product of the partial derivatives of r with respect to u and v. So here, for a parametric surface, a normal vector to that surface at any point is given by the cross product of the partial derivatives of the parameterization of that surface with respect to u and v. Now, a little more terminology to go with surfaces here. In the event that the normal vector is a non-zero vector, then our surface S is said to be smooth at that point. So that is if our surface has no corner. We could think about a corner as maybe the tip of a pyramid or a cone or something like that was what we would refer to as a corner. So as long as we don't have any points on our surface where we have a zero normal vector, then that surface is said to be smooth. So let's look at an example of finding a tangent plane to a parametric surface. So in this next example, we want the equation of a tangent plane to the parametric surface defined by the following vector function. At a specific point on that surface, 2, 3, 0. So we know in order to find a equation of a plane, we need a point, which we're given in the problem, and a normal vector to that surface. Now to get a normal vector to a parametric surface, we're going to take the cross product of the partial derivatives of that vector function. So our first step here will be to find the partial derivative of r with respect to u, which here would be given by 1, 6u, and 1, just differentiating each component function with respect to u. And the partial derivative of r with respect to v is given by 1, 0, -1. So a normal vector for our tangent plane, let's call it n, is given by the cross product of these. That is ru cross rv. Now to find that cross product, we're taking the determinant of a 3x3 matrix, whose first row consists of the standard basis vectors I, j, and k. Our second row would be the partial derivative of r with respect to u, that is 1, 6u, 1. And then the partial derivative of r with respect to v is our last row. That is 1, 0, negative 1. So finding this cross product, let's see what we have. For our I component, we have negative 6u minus 0. For our j component, we have 1 minus a negative 1, so 2. And for our k component, we have 0 minus 6u, so negative 6u. So we need to find the normal vector at a specific point on our surface. This vector defines a normal vector for any point on the surface in terms of the parameters u and v. So we're interested in this example we're interested in the point 2, 3, 0. Now let's think about what the parameters u and v are equal to in order to describe that point. So here, if we were to equate our component functions, the last component, 0, has to equal u minus v. So that means u and v are equal to each other. So then looking at the first component, we would have 2 has to equal u plus v. So since u and v are equal to each other, that means 2u equals 2. So u equals 1, and then since u and v are equal to each other, v is also 1. And we can see if u is 1, well, that middle value for y does indeed give us 3. So here at our point of interest, at the point 2, 3, 0, the parameter values for u and v are both equal to 1. And so our normal vector in, if we plug in u and v equal to 1, would be negative 6u, negative 6, 2, and negative 6. Okay, so now that we have a normal vector to our tangent plane and a point that it passes through, we're ready to find the equation of our plane. So recall, to find the equation of a plane with a given normal vector passing through a point, we take the first component of our normal vector, negative 6, times x minus the x-coordinate for our point, which was 2. Then we add the y component of our normal vector, which was 2, times y minus the y-coordinate for the point, which is 3, and then plus a negative 6, so minus 6, times z minus the z-coordinate for our point, which was 0, and that has to equal 0. So simplifying a little bit, if we distribute, we have negative 6x plus 12 plus 2y minus 6 minus 6z has to equal 0. So rewriting this in standard form, well, we can leave all of our variables on one side. We have negative 6x plus 2y minus 6z. And then moving all of our constants to the other side, well, we had 12 minus 6 was positive 6. So subtracting it to the other side, we have a negative 6. And then if we want to simplify a bit further, we see we could divide everything through by 2. So we would have negative 3x plus y minus 3z is negative 3. So this would be the standard form equation of the tangent plane to this surface at an indicated point. Okay. Now, another problem of interest when working with parametric surfaces is in determining their area. So we had looked at, we haven't seen in our course yet how to determine the surface area of a surface, which is the graph of a function. We'll see how to do that within this section. So let's talk about how to find the surface area of a parametric surface. Let's start by defining it. If we have a smooth parametric surface S, so that is it does not have a zero normal vector at a point, which is defined by the vector equation R of u and v, whose component functions our x, y, and z of u and v, where u and v lie within some domain D, and this surface S is covered exactly once as uv ranges throughout the domain D. So that is, we're not like overlapping this surface as we range through parameter values. Then the area of that surface S is given by, we'll call it A for area, and it's evaluated as the double integral over the parameter domain D for u and v with respect to A. And the function that we're integrating is the magnitude of the cross product of r sub u and r sub v. So that is the magnitude of the normal vector to our surface. If we integrate it over our parameter domain with respect to area, we get our surface area. So now that we have this, let's look at how we could find the area of the graph of or of a surface, which is the graph of a function of two variables, say z, which is a function of x and y. So here we want the area of part of this surface, z is x plus y squared, which lies above a triangle whose vertices are the origin, 1, 1, and 0, 1. So thus far, we only have a formula for finding surface area for a parametric surface. It involves finding partial derivatives of the vector function r with respect to u and v. So our first step here will be to parameterize this surface. So as we saw in our earlier example, if our surface is the graph of a function of x and y, then an easy parameterization is to simply let x be equal to u and y be equal to v, in which case z is then just the function in terms of x and y. So here we had x plus y squared, that would be u plus v squared, if x and y are set equal to u and v. And now we have our parameterization. So the part of this surface, r of u and v, could be given by this vector function, where the x component is u, our y component is v, and our z component is u plus v squared. Now let's think about our parameter domain. So here, u and v lie within a region D, and let's think about what this region D is. We were told that we want the part of the surface which lies above a triangular region in the plane. So here D is going to be that triangular region. Let's sketch it out. So within the xy plane, we're looking at a triangle whose vertices are at 0, 0, 1, 1, and 0, 1. So we're looking at the triangle shown here. And we want points that lie inside of that triangular region. So this is the sketch of D. So in order to find our surface area, using the formula that we've given, or the definition that we've given above, we need to find the partial derivatives of r with respect to u and v. So let's see what we have. Here, the partial derivative of r with respect to u would be 1, 0, 1. And the partial derivative of r with respect to v is 0, 1, 2v. Now we need to find the cross product of these vectors. That is r sub u cross r sub v. So to find that cross product, we're looking at the determinant of a 3 by 3 matrix, where our first row is the standard basis vectors I, j, k. Our second row is r sub u, which was 1, 0, 1, and our last row is r sub v, 0, 1, 2v. So if we find this cross product, our I component would be 0 minus 1, so negative 1. Our j component is 0 minus 2v, so negative 2v. And our k component is 1 minus 0. Now we need to find the magnitude of that vector to calculate our surface area. So here the magnitude of RU cross RV is the square root of the sum of the squares of components of those vectors, of that vector. So here our cross product had a first component of negative 1, so we take negative 1 squared, plus our second component, negative 2v squared, plus our last component, which was 1 squared. So altogether we are left with the square root of 4v squared plus 2. All right. So finally, we're ready to set up our integral for the surface area. So here the area of this surface is evaluated as the double integral over our parameter domain D of this magnitude of our tangent vector, which we just found to be the square root of 4v squared plus 2 with respect to a. So let's set this up as an iterated integral. So here, if we think about our domain D as being a type 1 region, we can think about the outer integral with respect to x, or with respect to u here, as ranging from 0 to 1. And our inner integral with respect to v, well, our v value is bounded above, or below, let's say, by the line y equals x, or using our parameters, v is equal to u, and it's bounded above by the constant value y equals 1, or v equals 1. So for our inner integral, we're ranging from u to 1, and we are integrating 4v squared plus 2 dv du here. Now the way that I've initially set this up was as an iterated integral considering D as a type 1 region. So here to integrate this inner function with respect to v, since it involves square root of a sum of squares, we would have to make use of a trig substitution. That gets a little complicated here. So instead of doing that, let's reverse the order of integration here to make this a little easier to handle. So if instead I think about D as a type 2 region, my outer integral with respect to V would be from 0 to 1. And our inner integral with respect to U, let's think about the bounds on U. So U could be bounded on the left by the constant x equals 0, or U equals 0, and on the right by the same line, y equals x, or U equals v. So our range of values for U would be from 0 to v, and our function is still the same, square root of 4v squared plus 2, now in the order du dv. So integrating with respect to u, well, we see that our inner function here, square root of 4v squared plus 2, doesn't involve u. It's a constant with respect to u. So when I integrate a constant function over an interval from 0 to v, I am left with the constant, which was the square root of 4v squared plus 2 times the length of our interval. So here from 0 to v, we have just v. And then we're integrating that with respect to v. So now to evaluate this integral, we can make use of a substitution. So here, normally we would let u be the variable for our substitution, but since we're using u as a parameter here, let's maybe make use of w instead. So we're going to let W equal 4v squared plus 2, in which case dW is 8v dV. So rewriting our double integral, or our integral for surface area in terms of W, we have a 1/8 the integral of the square root of W dW, and let's change our limits of integration here. So our lower value, when V is equal to 0, we see that W is equal to 2. And for our upper value, when V is equal to 1, W is then equal to 6. So integrating from 2 to 6 here. So let's see what we have. We have a constant 1/8 times the antiderivative of square root W would be 2/3 W to the 3/2 power, which we're integrating from 2 to 6. So simplifying here, grouping our constants, 1/8 times 2/3 leaves us with 1/12. When we plug in 6 for W, we have 6 to the 3/2, or 6 root 6, minus, when we plug in 2, we have 2 to the 3/2, or 2 square root of 2. So this expression would be the surface area of the part of that surface which lies above this triangular region D. Okay. So in our next example, we have a similar problem. We are asked to find the area of the helicoid, or sometimes called a spiral ramp, which is defined by the function r of u and v, whose component functions are u cosine v, u sine v, and v, where u ranges from 0 to 1, and v ranges from 0 to 4 pi. So here I've given the graph of this helicoid. So let's think about why, just without the graph being given, why we might think it looks like this. So if we had a fixed value of u, let's say that we chose, for instance, u equal to 1, that upper limit. If we plug in 1 for u, we have cosine v, sine v, and v, which would be a vector function of a single variable, so it defines a space curve. In that type of curve we've seen before, it is a helix. So here, if u is equal to 1, we would be sketching out the helix of radius 1 on the v interval from 0 to 4 pi. So we're moving twice around our helix here, as we're ranging from 0 to 2 pi, since sine and cosine are 2 pi periodic. And then the way that we get this surface is by the values of u varying. If we were to decrease the value of u from 1 to 0, well, we would be tracing out these other helixes, but of smaller radius. So we have these other helixes, which we're sketching out for different values of u. And as u ranges from 0 to 1, well, if u is 0, we're starting at just the positive z-axis. And then as u ranges outward, we're moving outward from that and tracing out at largest a helix of radius 1. So we end up with this spiral ramp figure shown here, or called a helicoid. So if we are interested in finding the area of that, well, it's given in terms of a parametric surface. It's defined by this vector function. So our first step to find surface area of a parametric surface is to calculate the partial derivatives of r with respect to u and v. So here, with respect to u, we would have cosine of v, sine of v, and 0. And differentiating with respect to v, we have a negative u sine of v, positive u cosine of v, and 1. So now we need to find the cross product of those two tangent vectors. So here, looking at RU cross R sub V, we're taking the determinant of a 3x3 matrix where our first row consists of the standard basis vectors I, j, k. And our second row is partial with respect to u. So we found those components were cosine v, sine of v, and 0. And our third row was the partial with respect to v, which we found as negative u sine v, u cosine v, and 1. So let's see what we get for our cross product here. For the I component, we have sine of v minus 0, so just sine v. For our j component, we have 0 minus cosine v, so negative cosine v. And for our k component, we have u times cosine squared v minus a negative u, so plus u, times sine squared v. So simplifying that last component, we have sine v, negative cosine v, and then if we factor out a u from that last component, we have the sum of sine and cosine squared, which is 1, so we have u times 1 for that last component. All right. Now we need to find the magnitude of that cross product. So here, the magnitude of RU cross RV is the square root of the sum of the squares of our components. So here we have sine squared v plus squaring the second component, we have a positive cosine squared v plus our last component squared would be u squared. So again, the sum of sine and cosine squared of v is just 1, so we're left with the square root of 1 plus u squared. So we're finally ready to set up our integral for the surface area. So here, the area of that surface is evaluated as the double integral over the parameter domain D of our function, which was the square root of 1 plus u squared with respect to a. So setting up this double integral as an iterated integral, well, here our parameter domain is just a rectangle in the uv plane. U ranges between two constants, and so does v. So if we set this up, we have our outer integral with respect to u from 0 to 1, and our inner integral with respect to v would go from 0 to 4 pi. We are integrating the function 1 plus u squared in the order dv du here. So as with our last example, this inner function 1 plus u squared is a constant with respect to v. So if we integrate, or if we pull that constant out in front, then I'm left with just a constant length of my interval 4 pi. So we have 4 pi times the integral from 0 to 1 of this square root of 1 plus u squared du. Now, this integral is actually quite difficult to evaluate. To find an antiderivative, well, we can't use a substitution here. We see that our antiderivative, or our integrand, involves the square root of a sum of squares. So we could make use of a trig substitution here. So if we were to use a trig substitution to evaluate this, we would let u, since we have the square root of a sum of squares, u would be equal to 1 tangent theta, and du is then equal to secant squared theta d theta, and our square root of the sum of these squares, 1 plus u squared, is then the square root of 1 plus tangent squared theta, which is secant squared. So the square root of secant squared gives us just secant theta. So converting this to an integral in terms of theta, we're left with 4 pi times the antiderivative of secant cubed theta, d theta. Here we're integrating from 0 to 1 for u, so that would correspond to a range of 0 to pi over 4 for theta. And then to integrate secant cubed, you have to make use of integration by parts twice. You get a loop integral that's a little bit difficult to evaluate. So here I won't go through the full detail of evaluating that antiderivative, but I will give you the antiderivative here if you finish this out. So we have 4 pi times, we end up with an antiderivative in terms of u of 1/2 u times the square root of 1 plus u squared plus 1/2 of the natural log of absolute value square root 1 plus u squared plus u. And we're evaluating with respect to u from 0 to 1. So let's see what we get here. My first step, I see that both of these terms in my antiderivative involve a factor of 1/2. So if I were to pull out a constant 1/2 with my 4 pi, that gives me a 2 pi times, let's see what we get when we plug in 1 for u. So we would have 1 times the square root of 2 is root 2 plus the natural log of square root 2 plus 1, which is positive, so I can lose the absolute value for that logarithm term. And then we subtract what we get when we plug in 0 for u. So plugging in 0 for u, I have 0 for that first term, plus the natural log of 1, but log of 1 is 0. So altogether, I have a 2 pi times the square root of 2 plus the natural log of square root 2 plus 1. So this would be the area of that spiral ramp figure. And here again, one difficulty, probably the most difficult part of this problem, is in trying to find an antiderivative of this function that we get after setting up our iterated integral. So that finishes the first part of our lecture on the section 6.6 material. We've defined a parametric surface, which is a surface described by some vector function of 2 parameters, u and v. And we've seen how to find tangent planes to these parametric surfaces at a point. And we have found how to calculate the area of these parametric surfaces. Now in the next part of this section, we will introduce the idea of a surface integral of a function of 3 variables. So that's similar to a line integral over a curve in the plane. Instead, we're going to integrate a function over some surface that lies in space.